Okay, so again, so we want to build a software computer system that learn and adapt from the past, from their past. So there are a few words we need to be we pay attention to. So in the end, what we're building is computer systems. We're building computer systems from data. So this is very important. So in the traditional software engineering, we use the software, right? As the engineer, we use rules or whatever logics to build softwares. But here, fundamentally different is we're building softwares based on the past historical data. So it's not from the programmers to build softwares. We're using data to build softwares. And the majority of cases, the past history or experience is in the form of available data examples. We're going to show example in the next page. And the available examples are mostly described by some properties, like maybe they're described by as data points in a feature space. Let's just call that feature space the real space. Real space may be RP. And we represent that real space RP, meaning let's assume all the input space, we use the notation capital X as the input space. Notation X representing the input space. So normally you want to do something, right? So the most classic task in machine learning is the supervised learning task. The fundamentally it's actually very easy. You want to learn a function. That function map data points from the input space X into a point in the out space Y. So that's why we write it as X to Y, and in the middle we try to learn that F function, and this F function is our software. So again, machine learning is about using data to build a software. Here, we represent that software as F function. So the simplest case of the F function is just a binary classifier. So whatever data inputs you give me, I want to split them, classify them into two cases. So more concretely, this can be, the X can be just a piece of English text. So in this case, is this something just copied from Amazon book review? I believe this book is not at all helpful, blah, blah, blah. So you labeled it into no, -1. You represent it as 1 represent yes, good review. -1 represent as no, bad review. So in this case, the X space is all the possible English text pieces. Y space is just a set. It's 1 and -1. I'm trying to learn a function to convert a piece of English text into a binary set. Pick one of them from that set. And the simplest question, actually, the F function form can be just this form. Okay, this green color may be hard to read. Can you read this green color? You can? Yeah, otherwise next time we'll change to blue color or red color. So simplest form. So assuming you can represent X into a two-dimensional space, just two-dimensional and or p-dimensional. So you just can write that separation function, separation software, into this form. W transpose X plus B plus a sign function before. It has this form if you draw this visually. So assuming this is the feature, maybe number of words, number of good words. And this can be some other features. Yeah, what can be a bit here? Bad features. So what you really learn is to, as I said, input space, we're representing past. We're representing past as data examples. Here, this is a past. This is one past, one case of past. A book review and a label. The label is the red color, and the position is that book review, which using that specific feature I like to describe, and then it converted into a data point into this R2 space. This is fundamentally simple, elementary, but also important. So again, this, I'm representing the examples as a point in this R2 space. So who tell me, yeah, I'm using real space now, but it can be other spaces too, right? But just now I'm using R2. And data points are labeled through the shape or color in this case. I'm trying to learn a function to separate the two colored points. And that function can be described very easily just through this form. W transpose x plus b and take a sign. Questions? And then the whole thing is, where do we put that function, right? Put that separation lines. Yeah, it's so easy. My eyes, put it there. Right? I use my eyes to put it there. But how do you let a computer use this group of data and that group of data to know, put a line there? What do I mean, put a line there?
Maximize the margin.
The next level. What I'm asking is, what do I mean put a line there is to do what?
Determining W and B.
Exactly. Because I have to determine what's the slope, what's the intercept. That defines this line, right? This is basic in algebra you learned in your high school or maybe 8th grade. Yeah, I think 8th or 9th grade you learned this. Okay? And this region is the double transpose x plus b larger than 0. If I'm doing sine function, that's discrete rounded into 1. And because this is smaller than 0, a sine function will assign the under the line into -1. That's exactly how this function represents. And what I mean, learn a program from data essentially means what? Using the points, red points and blue points to decide what is W, what is B. Questions? Okay, so W and B are my program. Plus this form, it's my program, right? It's a linear form, the unknown parameters is W and B. This is my f function. From data, I want to learn f function. Means what? Means I want to know this shape of the f function. In this case, I assume it and make assumption. That's a linear line. That's my assumption. And this form is part of the assumption, but also part of what my program really is. And then W and B is those unknown parameters specify the exact form of that program. So how do you search it? So in the end, you want to, so the whole thing can be summarized as, I want to find a program so that the difference between the y and the predicted fx of each example is super, super small. So what do I mean in this? I think we're class ends at 15, right? Okay, sorry, there's only 1 more minute left. So I'm using this bullet point and full point to learn where is the line, right? And that's my program, that's my software. My software is this line, and actually it's this form. When I'm using the software, we're all programmers, right? You write a good program, and then you test it. How do you test your program? You run some new examples, right? New examples are the inputs of your software. In this case, what is the input of my software? It's the position. There's a new point. I know their positions in the input X, right? I only know the position, but I do not know the labels. My program generates what? My program, because this is above the line, will give me a label class just from this function. So again, this program's input is X, output is Y. I'm using data to learn the program. Same thing as all the software, what we did before, right? Input, output, and the true program. The differences is how do you code that program? In this case, you need to code it. So you have some coding procedure there is you code it as a sign W transpose X plus B4. But there's wiggling parameters to make that linear separation lines truly fit my data well. And that's the one you need to use the past data to learn. Parameters of the program, input, output, and how you learn it is by finding the W and the B, minimizing something we call loss. Loss is just differences between Y and Fx on the available examples in the training data. So my Fx, on each example, my program will generate a Y, right? So on those data, I know the label. I actually just can compare the differences. And I do a sum over all the differences across multiple examples. That is the loss function. That is the error my program is making. I'm trying to minimize that error on the labeled data. Those data, I know the color are the data I call labeled data. Labeled data. In the end, I'm trying to look for the wiggling parameters of software, WMB, code that software to minimizing the error made on the training labels, on the past known labels. I think we're on the testing, but anyway, so I want to show one thing because I should have that. I should put that way before, gosh, okay. Give me a second. So I hope you maybe know about what expert training. In expert training, the most important something called mental representation. Whatever expertise you're trying to grow, musician, chess master, the athlete, whatever skills you want to be an expert, your mental, those representations you keep in mind about the skill is very important. And this is almost the most important centerpiece of this course, is the mental representation of machine learning. And this is it. So we always think about machine learning from class, representation, store function, optimization, and model parameters. So I did not go over everything there, but this is the mental representation. No matter what courses, what classes we are, use this to fit whatever we cover. Oh, that page is about task. Oh, this page is about representation. Oh, next page is about scoring function. We roughly covered, right? The task we covered is classification. The representation we covered is a linear form. And the scoring function we covered is something like sum of L. We did not cover